Okay, hi everyone. Our speaker today is Xavier Ramons Olivé. He's a postdoc at Worcester Polytechnic Institute, and he will give a talk called Geometric Analysis Under Integral Curvature Conditions. So,
thank you very much, and thanks to all the organizers for having me here today. So I'm gonna share my screen. Can you see my slides? Yes, right? Yeah. So today I'm gonna. Thank you. So yeah. So today I'm gonna be talking about this geometric analysis. Basically, I'm gonna be presenting some classical results in this area, some comparison results. And then in particular, we're going to be focusing on some more modern conditions, if you want, which are these integral curvature conditions. So since I have to talk about curvature, let me start there and let's discuss some notions of curvature. Okay? So we're going to be talking about Riemannian manifolds. So we're going to have a manifold. If you're not familiar, just think of some surface or some kind of n-dimensional object, submanifold of Rn if you want. And Riemannian just means that we have a smoothly varying inner product. We have an inner product at each tangent space. Okay, so at every plane you have a dot product. There's many different notions of curvature that one can study. So maybe one of the most intuitive ones is what's called the sectional curvature. Okay, so here you have a definition. It's not, the definition is not so important for us, but just I felt like I had to give a definition for it first. So the sectional curvature is defined on any two-dimensional plane. Okay, so you take two vectors in your tangent space. The sectional curvature is defined like this. So what you do is you plug in those two vectors into what's called the Riemann curvature tensor. Okay, this is an tensor that its three vectors spits out another vector. So you do this combination, you plug in two vectors into it, plug in V, and then spits out. If you do the dot product with U, this quantity here ends up being the sectional curvature. Okay, so this is the number. Actually, the number doesn't really depend on the vectors U and V. It only depends on the plane that the two vectors span. Okay, so at every plane you have a number, and that's the sectional curvature. All right, so here's the definition. What can we say about sectional curvature? So sectional curvature is actually a pretty strong notion of curvature. So for instance, we have a complete classification for what are simply connected manifolds that have constant sectional curvature. Okay, so if you have a simply connected manifold with sectional curvature equal to some constant k, then you have to be in one of these three cases. Either you have a sphere if k is positive, right? If you have positive curvature, you have Euclidean space if k is 0, or you have hyperbolic space if k is negative. Okay, so you're in one of these three spaces. These three spaces actually are sometimes just referred to like this. So S and K. Okay, and they're very important because we usually compare things to these spaces. So they're usually called model spaces. So these are gonna show up more and more. All right, so the kind of results that I want to present today are what are called comparison results, and you have an example down here, which is Bonnet's theorem. So Bonnet's theorem is a theorem from the 19th century. Originally it wasn't formulated in this way because at that time sectional curvature wasn't a thing yet. And Bonnet's theorem says that if you have a manifold whose sectional curvature is bigger or equal than k, so if you have this condition for k positive, okay, so we have a manifold that has positive sectional curvature. In particular, we're saying if the sectional curvature is bigger than the sectional curvature of a sphere, then the diameter of your manifold, here by diameter I mean the maximum distance between 2 points, this maximum distance between 2 points is going to be smaller or equal than pi over square root k. And what is pi over square root k? Well, if you think about the model space, here we are in positive curvature, so the model space is the sphere. Well, what is the diameter of the sphere? What's the maximum distance between 2 points in a sphere? It's going to be half of a circumference, right? So it's going to be pi r, pi times the radius. But a sphere that has curvature k will have radius 1 over square root k. So actually, this quantity here is pi over the radius of the sphere, and this is the same as the diameter of the sphere. Okay, so what this theorem is saying is that if you have a manifold that's curving more than a sphere at every point, then the maximum distance between 2 points is going to be at most the maximum distance that that sphere would have. Okay, so it's in that sense that this is a comparison result. It's a result in comparison geometry. Okay, so all the results I'm going to be presenting today are of this sort. Let's see. So I was saying this sectional curvature is more or less intuitive notion of curvature because actually in dimension 2, you're probably all familiar with it. In dimension 2, the sectional curvature is the Gaussian curvature, right? And actually that's the famous Theorem of Gauss. It really says that the Gaussian curvature in dimension 2 is the same as the sectional curvature. And so something that was initially defined extrinsically depending on the ambient space, it actually doesn't depend on the ambient space. It's an intrinsic thing. Okay, but sectional curvature is always intrinsic. It's defined only in terms of these tensors. So it's an intrinsic quantity. Okay, but I actually don't want to talk about sectional curvature so much today. I'm more interested in talking about Ricci curvature. So that's just another notion of curvature that we can discuss. And there's many different ways of introducing it, but here's the approach that I want to take, okay? So how do we find Ricci curvature? Well, imagine that you take some vector v, and now you complete that vector to a basis of your tangent space, okay? So here you have a basis of your tangent space. Assume that it's an orthonormal basis. Okay, well then the Ricci curvature of v comma v, the Ricci tensor is actually a 0-2 tensor. So you plug in 2 vectors to it, it spits out a number. So the Ricci curvature of v and v is actually, you can think of it as some kind of average of sectional curvatures. So what you do is you fix the vector v, and now for each of the other vectors in your basis, you consider the sectional curvature of the planes spanned by v and these other vectors. Okay, so you end up with this kind of sum of sectional curvatures, right? So this is some kind of average of sectional curvatures. Okay, so well, the reason I'm introducing it like this in terms of the sectional curvatures is because I kind of want to compare the two notions of curvature here. Okay, so the first thing that you can do is, well, just from this definition, you know that those model spaces that I mentioned earlier, the spaces that have constant sectional curvature, of course, are going to have here a constant Ricci curvature equal to n-1k, right? So this number here, n-1k, is gonna show up a lot in the theorems that I'm going to be mentioning, and you just have to keep in mind that that means that basically we're comparing the curvature of our manifold to the curvature of those model spaces. Okay, and in addition to that, we have that if your manifold has sectional curvature bounded below by some constant, then that means that the Ricci curvature is also going to be bounded below by n-1k, right? Just from the definition. Okay, so from this, what you can see is that actually having a sectional curvature bound is a stronger assumption than having a Ricci curvature bound. Okay, so sectional curvatures are stronger. So these kind of assumptions are stronger than the Ricci curvatures assumptions. okay, it's a stronger assumption because if you had a manifold, if you started with a manifold with sectional curvature, then automatically your Ricci curvature would have this lower bound. Okay, the opposite implication is not true, right? Just think about it in terms of averages, right? If you're, for example, if you have an average of a few numbers and the average is positive, that doesn't mean that each number was positive, right? So this is what's going on here. So just to show you a little bit an analogy of what I was mentioning earlier, if you have, so earlier we had this theorem of Bonnet that told us that if you were curving more than a sphere, then your diameter was bounded by the diameter of the sphere. Actually, the same theorem holds for Ricci curvatures. If you have a manifold whose Ricci curvature is bounded below by n-1k, and here k is positive, okay, so I'm comparing the Ricci curvature to the one of a sphere, then actually the diameter is also bounded above by the diameter of the sphere. Okay, so actually this is a stronger theorem. It implies Bonnet's theorem, and so because of this, sometimes this is also called Bonnet-Myers theorem. Okay, it's just a generalization into the Ricci curvature, which is, it includes a larger class of manifolds, so it's a better theorem. Okay, another kind of comparison result that I wanna mention before I get into the main topics of my talk are what are called volume comparison results. Okay, so anybody who studies Ricci curvature at some point has to study this. This is a very big deal, right? So there's a theorem that's usually called Bishop-Gromov volume comparison, that says that if you have a manifold with Ricci curvature with a Ricci curvature lower bound, so if you have this kind of assumption where here k could be positive, could be 0, could be negative. Okay, so as long as you're comparing it to one of those model spaces, then if you take two numbers, two radii, and you take a point in your manifold and a point in the model space, you have this kind of inequality between the ratios of the volumes of balls in of balls of different sizes. Okay, so what this is saying is that if you take the ratio of a large ball in your manifold and divided by the volume of a ball of the same radius in the model space, then that's going to be less or equal than the same ratio but for smaller balls. Okay. So this inequality here might, if you're not familiar with this field, it might seem kind of weird, but it's actually a very big deal. This is a very big deal, and it's very much non-trivial. So in particular, one of the conclusions that you can get out of this is what's called the volume doubling property, which volume doubling. So in particular, I'm writing it here for non-negative Ricci curvature. So what volume doubling tells you is that you can, at any point in your manifold, you can actually compare the volumes of larger balls. You can control them by the volumes of smaller balls. Okay, so if you have here P is a point in the manifold, and these things are just geodesic balls. Okay, and this says the volume of a large ball is controlled above by the volume of a smaller ball times this kind of ratio, right? And of course, it's called volume doubling because, in particular, if you consider this for a volume of twice the radius, you get this kind of inequality. Okay, so this is important because it's very much non-trivial. If you have ever studied what are called metric measure spaces, right? If you take a space with a notion of distance and a measure, there's no obvious way of relating the distance to the measure, right? Yeah, so this is what's happening here. I don't know if there was a question, maybe. Let me see if I can pull out the chat. Can a similar formula like volume doubling be obtained for k negative? Right. Yeah. So good question. So actually, this can be obtained. So what you can obtain for negative curvature is a volume comparison result but not exactly volume doubling. No, volume doubling doesn't quite work. That's just because, I mean, this volume doubling just comes out from computing what is the volume of balls in Euclidean space, right? And the volumes of balls with Euclidean space is just a constant times r to the n. But for negative curvature in hyperbolic space, the volumes of balls end up, I think they have an exponential term, so they depend exponentially on the radius. So then you don't end up with volume doubling. That's not true there. But at least you have volume comparison, which might be enough sometimes. Okay. Maybe the only thing I want to point out here is that these estimates and all the estimates that I'm going to be showing you today are uniform in the class of manifolds with these curvature assumptions. Okay, so if you see the constant here, this constant only depends on the dimension of your manifold, right? In general, if we could do this for positive curvature, that's, you know, volume doubling is still true for positive curvature. And then this constant would depend on the curvature and on the dimension, but it wouldn't depend on anything else. So that means that, you know, independently of what manifold you're picking, you can always compare the volumes of different balls at every point. Okay, and so that's the idea of these kind of results. We want uniform estimates on things. Okay, so let me move on to what I'm really going to be talking about today. I'm going to be presenting a few estimates on eigenvalues. Okay, so we're going to be studying what's called the Laplace-Beltrami operator, or the Laplacian for short, right? Acting on functions. Okay, so I'm gonna just define the Laplacian to be the divergence of the gradient, just as you do in Euclidean space, and we're going to be studying this eigenvalue problem. Okay, so we just want to find eigenvalues of the Laplacian. Okay, now if your manifold is closed, which means that, you know, it's compact and the boundary is empty, right? So compact and no boundary. So think about a sphere or a torus or whatever you want. Then, well, when the manifold is compact, we have a discrete spectrum for the Laplacian. So we know that we can arrange the eigenvalues of the Laplacian as a sequence. And if the boundary is empty, then the first eigenvalue, the smallest eigenvalue, is going to be 0 automatically, because you can just plug in a constant function. Right? Plug in any constant function is going to satisfy this equation with lambda equal to 0. Right? So there's a lot of interest in actually studying what is the first non-zero eigenvalue, this lambda 1 here. Okay. In particular, it's interesting to find upper and lower bounds for lambda 1, because those are related to many other inequalities in analysis. Okay. I'm going to be focusing on lower bounds for lambda 1, because upper bounds, you know, there's a variational formulation for lambda 1, and finding upper bounds is simple in some sense. Okay, because you can just basically you have the lambda 1 is an infimum of some ratio, right? And so you can just pick a test function to find an upper bound for lambda 1, whereas finding lower bounds is typically more difficult. Okay, so there's some very classical results on lower bounds for lambda 1 that only depend on these geometric assumptions that I was showing you earlier. Maybe one of the earliest results is due to Lignerovitz in the 50s, and the theorem of Lignerovitz says that if you have a manifold with positive Ricci curvature, okay, so here we have k is positive, and your manifold is more, you know, has more curvature than a sphere, then actually lambda 1 is going to be bounded below by kn, and this estimate is actually sharp because kn is the first eigenvalue of a sphere with constant curvature k. Okay, so so we see again this kind of comparison results, right? You have as assumption that the Ricci curvature is bigger than the Ricci curvature of the sphere, and then it turns out that your lambda 1 has to be bigger than the one of the sphere. Okay. Not only that, but actually Obara later proved that we have what's called the rigidity result, which means that, you know, if equality is achieved, right? If you have the lambda 1 is equal to kn, then actually your manifold is isometric to a sphere. Okay, so equal sign here means isometric. Okay, so not only diffeomorphic, but it's you have an isometry. It's really the same. It has the same geometry. Okay. All right. So this estimate of linear it's good. It gives us a lower bound. It's a uniform lower bound for the whole, for all the manifolds that satisfy this curvature assumption. But it doesn't tell us anything when k is 0, right? So if we are comparing it, for example, to Euclidean space, then this is only telling us that lambda1 would be non-negative, which we already knew. So actually, if you wanna assume, if you wanna be able to prove some kind of lower bound on lambda1, you're gonna need an explicit assumption on the diameter of your manifold. So if you have a manifold with non-negative Ricci curvature, and the diameter of the Ricci curvature is bounded above by some constant d, then actually Li and Yao proved that lambda1 is going to be bigger or equal than pi squared over 2d squared. Okay, so here Li is Peter Li and Yao is Xingteng Yao, which you might have heard of, right? The Fields medalist. Okay, so what's happening here? This additional assumption on the diameter, it's actually not really an additional assumption, right? Because in the case of Lignitz, when you had the positive curvature manifold, we knew from Bonnet-Meyer's theorem, we knew that we had a bound on the diameter, right? So when the Ricci curvature is positive, the bound on the diameter is automatic, okay? But if the Ricci curvature is non-negative, then the bound is not automatic, okay? Because you can consider Euclidean space. Euclidean space doesn't have any bound on the diameter. And fair enough, Euclidean space is not a closed manifold, and here I'm talking about compact spaces, but you could consider a torus, and you could consider a torus as large as you want, and tori can be constructed in such a way that they are flat, so that the Ricci curvature of a torus can be made to be 0, right? So that's why you need some kind of bound, okay? Otherwise this lambda1 you cannot obtain a lower bound for it, okay? Because as the diameter grows larger and larger, lambda1 actually goes to 0. Actually, this estimate is not sharp. The sharp estimate was obtained a few years later by Zhong and Yang, who were basically, they were actually visiting, they visited Yao in San Diego, and so they learned the technique of Li and Yao, and then they improved it. They just tweaked it a little bit, and using their technique with some improvements, they were able to find the sharp lower bound. Okay, this lower bound is sharp because this is lambda1 for a circle, for a one-dimensional circle. Okay, actually, so this is actually pretty easy to compute. If you if you ever wanna try it, you can compute the first eigenvalues of the circle. Just you can use polar coordinates and write the Laplacian in polar coordinates. You'll see that the first eigenvalue of the circle is 1 over the radius squared. The first non-zero eigenvalue is 1 over the radius squared. And if you have a circle of radius r, right, the diameter is going to be pi r. That's the maximum distance between 2 points, right? That's the diameter. So this quantity here, pi over d, is the same as, sorry, I don't know what I wrote here. Oops. Let me erase this. So this is wrong. Sorry, 1 second. Where's my eraser? Here. Sorry. The diameter is pi times r, right? So pi over d is 1 over r. And that's exactly what you have here. All right. So, and moreover, we also have a rigidity statement that's due to Hang and Wang, which shows that if the first eigenvalue is equal to pi squared over d squared, then the manifold is isometric to S1, okay, to a circle of diameter d, okay? So whichever circle will have that diameter, okay? All right, just for completion, let me just mention that there are also theorems that compare the first eigenvalue of the Laplacian with a model space with constant curvature, with negative curvature, okay? And for example, in particular, Yang has, there's different versions of it. Yang has this result, which recovers, it depends on the curvature here with this exponential term, and it recovers the Yang estimate in the limit when k goes to 0. Right? So it's good in that sense. But I promised that I would be talking about integral curvature assumptions, right? So let me sort of motivate the topic here. So see, these estimates are all uniform estimates, right? You have an assumption on the curvature, and then you have an estimate that holds for all manifolds with that assumption. Okay. These kind of estimates, you usually want them to be able to prove things on this class of manifolds, right? Or for instance, you might wanna use it to consider like sequences of manifolds. So imagine that for example, you have a sequence of spheres. Okay, you start with a sphere, and then you start pinching that sphere in some very small region. Okay, and so you consider this sequence of increasingly pinched spheres, and you want to see what's happening there, right? Now, all these manifolds, all these spheres are compact, and so because of this, you're going to have a lower bound on the curvature, on the Ricci curvature, right? However, as you pinch the sphere here, the Ricci curvature, what you're doing is you're introducing a lot of negative curvature there, okay? And so the Ricci curvature is basically blowing up as you keep pinching and pinching, okay? So, so because of this, you cannot find a uniform lower bound on, that works for all the sequence, right? And so because of this, you cannot apply any of the theorems that I showed you to this sequence of spheres, right? So the problem here is that you have a very small perturbation of the metric, very small perturbation of your geometry, and yet that small, so basically from a global point of view, when you look at globally at this manifold, this is basically a sphere, right? And so you would expect these theorems to more or less hold, and yet they don't, because you can't find a uniform lower bound. Okay, so in recent years, people have been trying to find curvature assumptions that are less sensitive to this, less sensitive to this kind of small perturbations of the metric. Okay, one way to approach these difficulties is by considering integral notions of curvature instead of pointwise lower bounds, right? Like here we had a pointwise lower bound on the Ricci curvature. Instead of that, you might want to define some kind of bounds in an integral sense. Okay, so here's a definition of what I mean by integral curvature. Okay, let me walk you through it. The first time you see it, it's kind of a little bit overwhelming. So okay, imagine you have a point in your manifold, and let's consider rho of x here to be the smallest eigenvalue of the Ricci curvature. Okay, so the Ricci curvature, you can think of it as a n by n symmetric manifold, matrix, right? N by n symmetric matrix, and so you can consider the smallest eigenvalue at every point, right? This matrix is changing from point to point, so so this smallest eigenvalue is gonna depend on the point that you're at, right? Now for a given constant k, we're gonna define the following function, rho sub k, which is defined like this. And what is this? So this function is actually it's a function that measures by how much this inequality is failing. Okay, so or Ricci is bigger or equal than n-1 k fails. I mean, saying this is the same as saying that the lowest eigenvalue rho is bigger or equal than n-1 k. Okay, and so what this quantity here measures is exactly by how much this is failing. Okay, so in particular, if the inequality is satisfied, then this quantity is negative, and so on the left hand side, and so the maximum of the two is going to be 0, right? So this function is going to be 0 if this is satisfied, and otherwise, if it's not satisfied, it's going to be this quantity is going to be the difference between these two numbers. Okay. So in particular, if k is equal to 0, then this is just the negative part of rho. In the sense of analysis, right? The negative part of a function. Okay. So once you have this function here, well, we can continue. We can define the following quantity, which is just you can take the LP norm or the average LP norm. Okay, here I'm taking the average LP norm of this function. Okay, this is going to be a number. It's going to be a number associated to your manifold, right? In particular, this is a non-negative quantity, and this number, if this number is zero, that means that the integrand was zero, right? And if the integrand is zero, that means that you had a pointwise lower bound on the Ricci curvature, okay? And intuitively, the idea is that if this quantity here is small, then we might be in a situation like this one, right? Like a situation where maybe, you know, your manifold is not, you know, doesn't really have a lower bound on the curvature, but the amount of curvature below that threshold is small, right? At least in some integral sense. Okay, so you have to think of this n-1k as being some kind of threshold. Okay, so if here you have here your manifold, and here you have the Ricci curvature, right? So here's the kind of like the profile of your Ricci curvature. What we're doing here, let's see, is we're setting a threshold at n-1k, and we're measuring all these amount of curvature, right? This is what this quantity is measuring. Okay, like how much the curvature is small. All right. So maybe the first person to consider these kind of integral curvature assumptions was Galois in the 80s, who proved some Sobolev inequalities. So Sobolev inequalities, basically, the important thing there is that the constants of those Sobolev inequalities only depended on these curvature assumptions. So they were Sobolev inequalities whose constants were valid for, you know, uniformly across all the manifolds with these kind of assumptions. And then I also want to mention that the work, you know, the very important work of Petersen and Wei, who were able to generalize this notion of volume comparison that I mentioned earlier, the volume comparison from Bishop and Gromov, into this setting. Okay, once you have, so as I said, once you have volume comparison, that's a very big deal, because suddenly you can volume comparison is fundamental for doing analysis in general. So once you have that, you can actually prove a lot of things. Okay. So let me just show you some, give you some flavor of some previous results on this kind of curvature assumptions. So first of all, I want to start with the result of Galois and later also Petersen and Sprouse. Galois and Petersen and Sprouse, they all proved Sobolev inequalities, where the constants depended only on these kind of curvature assumptions. And from there, you can actually derive an estimate on this lambda 1, on this first non-zero eigenvalue of the Laplacian, as follows. So if you have a closed Riemannian manifold, again, we're going to assume that you have some diameter bound, and then just for technical reasons, we're going to assume that P is bigger than n/2. So P was is the power that appears here, right, for the integral curvature. Then there exists an epsilon, and there exists some constant, such that if the amount of integral curvature below the threshold is less or equal than epsilon, then you have a lower bound on lambda 1. Okay, a uniform lower bound, right? Because this lambda only depends on the geometric parameters, not on the specific manifold, right? Only on the geometric conditions. Okay. The estimate of Galois and Petersen-Sprouse is not sharp. Okay, this constant is not sharp. The first sharp version of an estimate here on lambda 1 is due to Aubry in 2007, who generalized the estimate of Lignerovitz that I showed you earlier. Okay, so Aubry basically showed that in the positive curvature case, you have this kind of bound, okay, where lambda 1 is bigger or equal than nk times 1 minus a multiple of the amount of integral curvature that you have. Okay, so in particular, if the amount of integral curvature is small, then you almost have the sharp estimate. Okay, and in the limit where you have where this is 0. So if you have a pointwise lower bound, okay, the Ricci curvature is bounded below by n-1k, remember that then this k bar is 0, and so this quantity wouldn't be there, and you would recover the estimate of Lignit-Ovitz. Okay, so that's lambda 1 is bigger or equal than nk. All right. Now, just as with Lignit-Ovitz, this estimate doesn't really tell us anything in the case where k is equal to 0, and it took some time before before the estimate for k equal to 0 was generalized, and this was done in a joint work with Shosiro, Gofang Wei, and Qi Zhang. We finished this in December last year, December 2008, I think we finished. So, and the theorem basically says the following. So if you have a closed Riemannian manifold and you have diameter bound, then for any alpha and for any p bigger than n/2, again, some technical reasons, there exists an epsilon such that if the amount by which the inequality Ricci non-negative is failing is small enough, then lambda 1 is bigger or equal than alpha pi squared over d squared. Okay, so remember that pi squared over d squared was the sharp constant. Okay, and so what this is telling you is that the role of alpha here is just to say, okay, how good of an estimate do you want? How close do you want to be to the sharp estimate? You choose a parameter alpha, and then for that alpha, there is an epsilon such that if the amount of Ricci curvature in integral sense is smaller than that epsilon, then you have lambda 1 is bounded below by that. Okay, so in particular, in the limit where you have the pointwise curvature bounds, this k bar is 0, right? So this assumption is always satisfied for any epsilon, right? So for any alpha, this is always satisfied. So you always have this for any alpha, and so taking alpha, taking the limit as alpha goes to 1, you recover Yang. So it's in that sense that this estimate is also sharp. Okay. So let me just mention that the reason that it took some time to prove something like this is because the original proof of Li and Yao for this kind of eigenvalue estimates, it relies very strongly on a pointwise lower bound on the Ricci curvature. Okay, you have to prove an estimate on the gradient of the eigenfunctions, and it took some time to figure out exactly how to handle these kind of integral curvature conditions and mix them with the gradient estimate technique. Okay, it wasn't until the work of Zhang and Zhu in 2015 and 16 that people figured out a way of proving these gradient estimates for integral curvature. Okay, and maybe just to finish, let me just say that here I've been assuming in all these theorems that the amount of integral curvature was small, right, and not only bounded but actually small. And actually, this is actually a necessary condition, right? It's not, the result is not true if you just assume that the amount of Ricci curvature in integral sense is bounded. Maybe the way to see it is actually using a very classical example from Calabi, which actually I don't know exactly what the paper of Calabi is. I've seen this example in a very famous paper of Chigger. But basically what Calabi does is it considers a sequence of dumbbells. So this kind of shape, okay? A dumbbell, you don't know, is like some pesos, okay? Pesos del gymnast, no? So this kind of shapes here. And so what Calabi does is it considers a sequence of dumbbells with, that are joined here with a small cylinder of radius epsilon. And it's easy to show that these surfaces, as epsilon goes to 0, well, actually, their first eigenvalue is bounded above by a constant times epsilon. And so as epsilon goes to 0, you get a sequence of surfaces that whose lambda 1 is going to 0. Okay, and so what's happening here is that, well, from a classical point of view, what's happening is that you don't have a lower bound on the curvature because there's negative curvature in these regions. curvature in this region. So you cannot apply the Linearovitz estimate or the Yang estimate here. From our perspective, what happens is that although you could do a construction where the integral curvature is uniformly bounded along the sequence, it's uniformly bounded, but it cannot be small. It cannot be made small. Okay. And so that's what's happening there. And actually, I've been it's not completely obvious that you can construct these dumbbells in such a way that this is uniformly bounded. So I've actually been working with some undergraduate students doing research on this. I told them to help me construct an explicit, make an explicit construction of these dumbbells to see that exactly that you can do it in such a way that this is uniformly bounded, and yet that this gives a counterexample to dropping the smallness assumption. Okay. And this is all I wanted to present. So thank you all for listening, and let me know if you have any questions.
Thank you very much, Xavier. Thank you very much for this talk. If anybody has a question, you can ask it.
I do have a question. Maybe it's not directly related, but a little bit at least. Do you know if there are maybe some results in this direction, but instead of saying something about the first eigenvalue, maybe saying something about the eigenfunctions of the Laplacian, like taking some assumption on the metric?
Yes, there are results that study the eigenfunctions. I'm not that familiar with them. I could look into it. I'm not sure. On top of my head, I don't know right now. But yeah, you mean like some kind of comparison results between the eigenfunction?
Yeah, I don't know. I had in mind, for instance, there's this theorem of Uhlenbeck where he says that for a generic metric, the eigenfunctions are always like Morse, for instance.
Right. I'm not entirely sure. My guess is yes, but I'm not that familiar with the literature in that sense.
Thanks.
More questions?
Hi. Can you go back to your main?
Sorry, what was that?
Sorry.
Could you go back to your main result?
Oh, yes.
So I was wondering, do you think it's possible to get a similar bound, but in a way that on the right-hand side you have a bar? Because right now it's sort of qualitative in the sense that, for every alpha you can get some epsilon such as this thing. I was wondering if some sort of more quantitative.
Right. So so something more on the lines of this, right?
Yeah.
On the lines of this. Intuitively, yes, but in practice, so I think you could write this result in terms of this alpha ends up basically it's all interrelated. So the fact that you're not getting exactly the sharp estimate, but you recover it in the limit, it is related to this k-bar. It's just that the estimate, the exact expression is quite complicated. Actually, it's quite involved. So I would say that it might be possible to write it out in terms of k-bar, but it's very involved. That's why we decided to state it like this.
Okay, thank you.
Okay. So if there are no more questions,